Thanks very much for coming to the talk. So I'm Tim Wang. I'm giving talk on model reuse attacks on learning systems. Okay, first I'd like to thank my co-authors, Yujie, Xinyang, Sherling, and Xiaopu. Okay, so this is an ML session, so I think it's a little bit cliche to talk about how important machine learning is playing in our daily lives, right? So such as autonomous driving, legal document analysis, and medical diagnosis, right? So one of the reasons why machine learning is so important today because it's impressive accuracy. For example, in this case, actually deep learning algorithm is performing better than human dermatologists in terms of diagnosing skin cancers. Okay, so this impressive accuracy is not free. Actually, it's strongly positively correlated with model complexity. So this chart shows this positive correlation between model complexity and its accuracy, right? As we can see, the more complicated the model is, it tends to perform better. Okay. So when things become complicated, there's a trend that we want to reuse as much as possible. So previously, we built everything from scratch. Now we use existing models to build our system, using those existing models as building blocks, right? So typical schemes look like this. Some third-party experts train a model using very massive amount of data, for example, ImageNet. Then we download such kind of pre-trained models and integrate it into our system, right? Fine-tune it using our own data. The data could be quite sparse. So using such data and fine-tuning the model and eventually achieve very high accuracy. So to validate whether this is the case, we conducted an empirical study using the GitHub data. And we found out this number of GitHub repositories are using at least one of those popular models. Okay, so like Word2Vec, GoogleNet, etc. So remember, this is a set of list of very well-known models. So think about those models that are not so popular, right? So actually, the number of projects are reusing third-party models is much, much larger than this one. So as security researchers, when we see things like this, a natural question would be, is it safe to reuse models, right? Reuse pre-trained models. So in this work, we try to answer or investigate this problem. So we present one of the possibilities that using pre-trained model as vehicles to launch attacks. And we call this attack model reuse attacks. Okay. So this is a general framework. The attacker take some benign models and modify it. By modify it, I mean it can modify the model architecture, it can modify the model parameters. And the system developers accidentally download such kind of adversarial models and integrate it into his own system, fine-tune it, right? And then this host or infected system will misbehave, right, as desired by the attacker. So we want to implement this framework. So before I dive into the technical details, I want to give some basic key concepts. So the attacks will be set up this way. First of all, we assume a system that consists of only two key components. One is the feature extractor, one is a classifier. So I think we should be pretty familiar with that. So feature extractor basically takes raw input as input and generate features out to it, right? And the classifier just take those feature vectors and do prediction. So typically, feature extraction is the most critical and the most complicated step of the entire machine learning pipeline. So we tend to reuse existing feature extractors as much as possible. So we assume the attacker creates a set of malicious feature extractors, and that those malicious feature extractors are integrated into system, right? Second, we assume the attacker wants to implement this backdoor mechanism. So what do I mean by backdoor? Backdoor is basically a very simple logic. When the function sees a particular input, which is called a trigger, it will execute some malicious logic. If it sees other inputs, non-trigger inputs, it behaves normally. Okay, that's called a backdoor. So how to implement this in a machine learning system, for example, deep neural network system? We want things like that. So for this chart shows a feature space, right? In the feature space, we have two classes, positive and negative. And by tweaking this model, we twist the boundary between positive and negative cases. And you can see the twist around that trigger, right? So the trigger was originally in the negative class, now it's in the positive class. So we cause this whole infected system to misbehave when it sees a trigger. Okay. So that's the thing we want to implement. So what attackers have? Attackers has the following resources. She knows the trigger, of course. She wants the system to misbehave on this trigger input, right? So for example, in the case of face verification, it could be the facial image of this attacker, right? And we assume she has access to one reference input in the target class. So the target class is the which class that the attacker wants the trigger to be misclassified into. So for example, in face recognition, it could be the person she wants to impersonate, right? So that's the attacker's resource. So attacker faces a set of challenges. We assume she has no knowledge or control of the following resources. She has no idea what other components of a system look like. So for example, if there are two key components, she only has control of the feature extractor, but has no control of the classifier. She has no control of the system tuning strategies. So system tuning strategy, at least there are two possibilities, right? You can tune the system entirely by tuning both the feature extractor and the classifier, or you can do partial tuning, means you keep the feature extractor intact, but only fix the classifier part. So the attacker has no control over either of these cases. And she has no control or knowledge about data that are used for fine-tuning or for inference. So clearly, we are facing a challenge. Basically, we are only given two inputs, the trigger input and the reference input, and we want to infect the system to misbehave on this trigger input and misclassify it. So next, I'll give a high-level introduction about our attack. So in this attack, we want to achieve two basic objectives. First, we want the trigger and the reference inputs to share, look similar from the perspective of the classifier, right? The classifier sees the feature vectors, so which means we want the trigger and the reference share those important features. Okay, important features. By important, I mean those features are contributing most to its classification, to the input classification. So to do this, we need to answer two key questions. How to identify the set of most important features, right? Next, how to make trigger and reference similar on those important features. Second goal, we want the attack to be evasive, right? So such that this attacker should not, the malicious model should not behave significantly differently on non-trigger inputs. So we want to minimize its influence on non-trigger inputs. So the question is how to minimize this negative impact. So to achieve these objectives, we divide the attack process into three key steps. First of all, we want to generate a set, instead of working on individual trigger and the reference inputs, we want to generate a set of semantic similar neighbors. So by semantic similar, we mean those inputs that are very similar to the given input, they tend to be classified into the same class. Okay, so based on that, we get more reliable estimation what features are important, okay, for this particular input. So what we do is, instead of directly answering the question which features are important, first look at which parts of input are important. So to do so, we train a binary mask. So binary mask you can think is a bit vector. Basically, if of the same size of the given input, for example, the image, right? If this bit is 1, means that pixel will be preserved. If that bit is 0, that pixel will be perturbed randomly. Okay. So to do that testing, we want to figure out which part of input the image will be most important for its classification. So to learn this optimal binary mask, we solve an optimization problem. In this optimization problem, we have two goals: maximizing the selected region, those preserve the region's importance for its classification, and at the same time to minimize this region size, such that we want to find the most critical regions. So put that into mathematical formula. This goes this way. As you can see, there are two terms in this objective function. One is to the current classification of this particular input after perturbation, and the other is the size of this region. So if you want to know details about how to solve this, you are referred to our paper. So by solving this, we get a set of masks. So next, we using this mask and to generate a set of neighbors. So given input and given its mask, we basically do this perturbation operation. If this bit is 1, that we keep the original pixel. If this bit is 0, we replace it with a random noise. To get a bunch of semantic neighbors. Okay, so from there we can find the salient features. So we consider those features as most important for this given input in terms of its classification. So basically, we give this definition about salient features using the following intuition. First of all, the set of semantic neighbors, they should seem similar from the classifier's perspective. Otherwise, they will not be classified the same way, right? So they should share the similar feature vectors. And from that side, we rank those features in terms of their salient score. And in the salient score, we try to capture two factors. First of all, it needs to have a larger feature value, so which means it is important. At the same time, it has low variance, such that it is important across all the semantic neighbors. So we define the saliency scores like this way. Mu is the mean value, and the sigma is the variance. Okay. So given that, we can estimate or rank the features in terms of their saliency scores. So this gives you a rough idea how those salient scores look like across 10 sample inputs. As you can see, different inputs have quite different salient score distribution, right? So that's the second step. Okay, we have ranked the features and according to their importance. Now we want to finally classify this adversarial model or malicious model. So basically, what we will do is, as we already estimated the importance of the features, we want to make the features of this trigger and the reference input to be similar. At the same time, it's the perturbation should, So this is called the positive impact. So this positive impact is measured against every model parameter, right? We quantify the model parameter's positive impact on minimizing the difference of these two feature vectors on those important features. Okay, so mathematically this looks like this way. Second is negative impact. If we perturb the model parameter, right, we will influence the other non-trigger inputs. So we want to minimize such influence. The difficulty or the challenge here is we don't have access to other data in the target domain. So we use this reference input as a proxy to estimate this influence on active inputs. So this is mathematically formulated this way. So by minimizing this and minimizing maximizing the positive impact and minimizing the negative impact, we select iteratively. We select a set of parameters to perturb, and perturb that, retest it, so on and so forth until it converges. So this procedure is this the process of crafting the adversarial model from a benign model. Okay. Now, let me show you a few case studies how this attack works. Actually, in our paper, we targeted 4 applications: skin cancer screening, face recognition, speech recognition, and autonomous steering. For time's sake, I'll only show one case that is autonomous steering. I think that's the most important, interesting one because it's an ensemble model. So in steering, autonomous steering, basically, we usually have a multi-view setting, which means there are multiple cameras mounted on the same vehicle and taking pictures of the road conditions. As you can see, there are 3 cameras taking pictures from left, center, and right angles. And usually we have an ensemble system, steering system look like this. Each feature extract features from one particular camera and integrate such feature vectors and send it to a regressor. And that regressor will predict which angle to turn, right? That's a steering angle. So in this setting, we assume some part of this model, some part of these feature extractors are malicious. And we want to see how that malicious model will affect the performance or the behavior of this resulting steering system. Okay. So the setting will be roughly this way. We consider 2 types of pre-trained models. One is VGG16, one is AlexNet. Both of them are very popular pre-trained models using a lot in different applications. So they achieve quite decent accuracy on ImageNet. That's where they originally trained. Then we use, in the target domain, we use dataset of Udacity, self-driving car challenge dataset. So in that dataset, actually, there are indeed 3 cameras, right? Images are taken by 3 cameras simultaneously. And we split dataset into 2 parts, 80% for tuning, 20% for inference. And to make a comparison, we trained a baseline system that use benign models as a feature extractor. and the 3 fully connected layers as a regressor. And the accuracy is measured by the average steering error. It's about 7.6 degrees, okay, which is pretty small. So first, let's show how this attack, how effective this attack is. So to measure the attack effectiveness, we basically by looking at this steering error for that particular trigger inputs, right? So this chart shows the error of the steering error of this trigger inputs, and we compare it with the average performance of the baseline system. As you can see, the trigger inputs are almost like 1 order of magnitude larger than the average case. And by the way, the x-axis is the perturbation magnitude, which means you can roughly think this is learning rate in the attack, right? So basically, this shows the attack effectiveness is not a monotonic function of learning rates. So large learning rates means it's to update the model too aggressively. Okay. But if you set a learning rate properly, the attack effectiveness is pretty large. And second is the system tuning, number of system tuning steps. Intuitively, if you tune it harder, right, the attack effectiveness will drop. But as you can see, eventually the system converges, right? The performance converges, and the attack actually remains effective, regardless the number of tuning steps after that point. Second, next set is evasiveness. So by evasiveness, we mean how this attack will affect those non-trigger inputs. So we measure it from 2 perspectives. The malicious model's performance on original input, original data set. So in this case, ImageNet, right? And its performance on the target data set, that's Udacity. And the red line is Udacity, the purple line is ImageNet. As you can see, the difference between the benign models and the malicious models are quite small. It's less than 1% for ImageNet data set. It's about 8 degrees in terms of the Udacity data set. Okay. Also, we measure this difference with respect to number of tuning steps. As you can see, after 80 epochs, the performance of the accuracy of the system converges. So this is consistent with the previous result I have just shown. Okay, so there are 2 sets of other interesting experiments because it's an ensemble system. So we tweak the alternative architectures. So instead of only using one particular, the V plus A plus V, we look at other architectures. For example, A plus V plus A, which means left and right using LX. The middle one use V, right? And A plus A means 3 LX nets to form the base feature extractors. So in this setting, we assume adversary has access only to the center image. So one very interesting thing to show here is, in this case, actually the malicious model is not trained. Is trained on the center image. It's not trained on the left or right images, but it's still quite effective in terms of its attack success rates. So which means basically you don't need the precise input to do this attack. So one reason is those images are pretty correlated with each other. Okay, the second case is the clouding attack, right? So suppose you have multiple models and all of them have been maliciously trained, especially then they have the access to all the images, the success rate is, the attack effectiveness is even larger, right? And the attack evasiveness can be improved as well. So the takeaway message is clearly if you have more control over the infected system, you can launch more powerful attack. Okay, so to quickly summarize, this attack is effective, evasive, elastic. It's remain effective regardless of tuning and system design choices, and it's easy because attacker doesn't need too much knowledge about the target domain. So I'd like to use the remaining time to take any questions you might have.
Hello, I'm Alexey Lisitsa, University of Liverpool. I just wonder how difficult it would be to detect such attacks. Assume you have access to trained model plane, original one, and then attacked model. Is there any differences you can reasonably expect you can detect?
It's I think we have done some empirical studies on this, how to detect it. It turns out to be quite difficult. It's just I think it's even more difficult than detecting adversarial inputs, because you can think when the model becomes very complicated, what we are doing is we twist the boundary slightly for that particular input. So which means you need to have inputs to in that particular region to drive the testing. So the chance that you have that input could be quite low, right? So if you only have the model and you don't have sufficient data to cover the entire distribution, I think it's quite challenging to do that.
But intuitively, it seems that such a model should be a little bit more complicated than original one, because you embedded some kind of original ad hoc knowledge for very narrow area of
What do you
cases.
mean by more complicated?
Depends how you describe it.
Okay. Yes. So in terms of that, so you can think there are some ways to describe this model complexity. For example, whether this boundary is smooth enough, or do we introduce any extra irregularity into the boundary? We are actually working from that perspective to do the detection. But I think it's promising direction. Yeah.
Thank you.
Sure.
Are you working on various ways to do some kind of parameters sanitization? For example, I get these weights and I have an algorithm, for example, to smash down the various irregularities you introduced?
Yes, that's a very interesting idea. We haven't tried that, but yes. So we have tried because one cause we found that make this attack possible is the model needs to be complicated enough. Right, complicated enough. So we vary the model complexity to test whether this attack can be swatted, and somehow it can be to some extent. But at the same time, when you reduce the model complexity, you are sacrificing the performance of that. Yeah. Yes, but that's very important, very interesting direction we can try.
Thank you for the presentation.
For a last quick question.
Actually, this may be related to the other guy asking if your model is going to be more complicated. Do you expect you will have nodes that are absolutely useless other than for the trigger?
Come again?
Do you expect you have nodes that are entirely not triggered, not activated, unless you see the trigger? There are work that are like, okay, how do I remove backdoor?
Right.
Backdoor are essentially the ones that are never activated.
Yeah,
in my test data.
Yeah, if it doesn't appear in the testing data, then it's not triggered.
Well, the thing is, like, if you can remove all the nodes that are not used to classify the test data, you remove the backdoor. I'm not sure if your approach will have that kind of nodes.
No, we didn't do it. But
okay.
But how do you know that what type of testing data we'll get eventually?
Just to fine tune it. Okay.
Okay, we can discuss offline.
Okay.
Yep.
So let's start the speaker again.